Hello. Today's lecture is application of tropical P-Basel-Stein metric into a quantum information theory, or application the P-Basel-Stein metric into a matrix algebra. Before to this talk about main topic, let's recall that the previous lecture, P-Basel-Stein metric in a tropical projective torus and probability measure. Okay, in a probability measure space, in very general definition, if x, mu, and two probability measure space is given, the P-Basel-Stein metric is defined by the infimum in that case, okay, P and d mu d nu and 1 over P, and take, in this case, mu xy 1 over P, and that is lives in that correspond to the set of all couplings of two measures mu and nu. But as you see, that concept, okay, P-Basel-Stein matrix measure estimates between two probability measure. So that, however, that is so abstract, difficult to understand when we consider optimization or optimal transportation. Why that concept is related to this idea? To understand why this is related to optimization, we try to translate, if we translate a language in a tropical torus, projective torus, we can understand why this is related to a optimization. In a tropical geometry, as you see, if xy lives in a tropical projective torus, that is not original, that is not a definition, but by proposition, in a previous lecture, we can express the tropical metric is written as like this. Okay. In that case, gamma xy is corresponded to collection of all curves which passes through x, bar x. Bar x means initial point. And we can parametrize that, that is a V0 and y, that is terminal point that is correspond to Z in this case, G1, and G, if we different, you can compute GT is correspond to VT. Okay, I explained in the previous lecture. In that case, if we find a common denominator between two concepts, mu and mu is fixed. Okay, that guy is fixed. In a tropical geometric, tropical projective torus, 2 points x and y are fixed. Okay, that is fixed. And in case of the collection, in a probability density, in a probability metric, probability measure, I will not pi. Anyway, gamma is okay. In the previous lecture, I described that is large pi. That is set of all couplings, mu and nu, and in a tropical geometric language, that is correspond to collection of all passes. If we describe that situation, Rn plus 1 divided by R1 is given, we can choose bar x and bar y, and collection of all passes between bar x and bar y. So if we choose that curve that is contained gamma x y. Okay, and in a probability space, dxy means a distance between sampling spaces. So if a omega is given, x is given, choose a sample an element in omega, in that case, mu omega, because that is sigma algebra, we can correspond to measure. Think about a measure, mu omega and mu omega. So in that case, dxy is correspond to distance between sampling spaces. If you cannot understand this, then let's translate the idea into a probability space. In that case, correspond to LTR VT, which means that LTR is a tropical Lagrangian or tropical norm. That corresponds to a velocity vector. Okay, a velocity vector speed that corresponds to speed. The length of the velocity vector. Okay, so that idea is correspond to speed. So if because that guy is a speed, we can compute if the length of the curve L gamma, if parameterized at variable t, that is written as LTR Vt dt. That corresponds to distance, length of the curve gamma. Okay, and that is in fact in previous lecture, that is correspond to tropical metric like this, and infimum value. O gamma, but it is also holds for P LP norm sense. So we can take P and 1 over P. Okay. So that means that geometrical meaning of the P-Wasserstein metric, as you see, if 2 points is fixed, bar x, bar y in a tropical projective torus are fixed, P-Wasserstein metric means the length minimizing curve okay. So in this sense, in this regard, P-Wasserstein metric is related to optimization or so-called optimal transformation. Okay. In this regard, if you think about P-Wasserstein metric, in general, if x, y joint density probability density function, that is written as, in the previous lecture, that is written as blah 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 blah. That means that the risk gap between two probability density probability joint distribution density function. So if in a measure theory, a statistic learning theory, as I said, Wasserstein metric is to estimate, one way to estimate between two probability density functions. So the gap is, if the gap is smaller, the model between the true model and estimated model, then the the gap is smaller, that is a nicer model. Okay. That is one way to distance between two metric, two probability density function. And that if we understand that is optimization, let's go back this here. We can see that situation geometrically.